The zoo question, this one? Okay, all right. We will have a look at this. Okay, everyone, let's begin then. Assalamu alaikum. So we're doing mensuration today. We're done with all the concepts, pretty much all the concepts. There are a couple of things that I would cover today before doing some past paper questions. But let me quickly remind you about what we've done until now in 3D shapes in particular. We've talked about volumes and surface areas of all of these different shapes: cube, cuboid, cylinder, prisms, various kinds of prisms like this, right? Cone, pyramids, and finally sphere and hemisphere. This is what we have talked about until now. These are all the different standard shapes that you need to be able to find volumes for and also surface areas for. All right. And then we talked about what happens when you have similar figures. You can use these relations in similar figures. First of all, the ratios of corresponding sides are always going to be equal to each other. So if you have some radius and you have some length, some height, the corresponding sides of similar figures, they are going to have the same ratio. And when they talk about areas and volumes or masses, then for them, we have these relations for the ratios of areas. The ratio of areas is the same as the square of the ratio of sides. Ratio of volumes is equal to cube of the ratio of the sides. And similarly for mass as well, it's equal to cube of the ratios of the sides. That's what we've talked about until now. Now, there are two other kinds of shapes that you will see in the questions. One is something that we call a frustum. This is another shape that you have. This is a shape that is made by taking some part of a cone out or sometimes some part of a pyramid out. So if you look at this figure, it was basically a cone initially. So if I were to extend this side like this and extend the other side like this as well, this big figure, if you were to extend these sides like this is basically a cone. And what they've done is they've taken out this smaller cone out of this, and that leaves you with this shaded part at the bottom. And sometimes what you have to do is you have to find surface areas or volumes of shapes like this. Now, how would you approach this? Since this particular frustum, it's made out of a cone, so you had this bigger cone, right? If you had to find the volume of this cone, what can you do for that? You have the formula for that. For the bigger cone, you can say that this is the height, right? This is the height of the bigger cone. And then you have the smaller cone that's taken out of that. So this is a smaller cone that has been taken out of that. Let's call this H2. The bigger cone has a radius, let's say that's R1, and the smaller cone has a radius, let's say that is R2. If you had to find the volume of this frustum, what you would have to do would be, you would say it's equal to the volume of the bigger cone. So this bigger cone, you find the volume of this bigger cone, and you subtract from that volume of the smaller cone. Okay. And similarly, if you had surface area to find in this case, for that as well, you could find, the surface area of this prism, this would basically have three different faces, this frustum, not prism. If you had to find surface area in this case, if I were to copy this here, for surface area, you would have three different faces that you would have to add. One would be this circle. You can find the area of this circle, and then you can find the area of this circle. You would have the radius for both of them. The third part is going to be more complicated, and that's the curved surface area of this part. For the curved surface area as well, what you can do is you can find the curved surface area of the bigger cone, subtract from that the curved surface area of the smaller cone, and that will give you the curved surface area of this cone. So if you have to find the curved surface area, that's the area of this region. For that as well, you do something similar. You would say the curved surface area of this frustum, that is equal to the curved surface area of the bigger cone minus the curved surface area of the smaller cone. Okay, so when you have a frustum like this, what you do is you break it down into two parts like this. You have a smaller cone and a bigger cone, and you find the difference to find the volume of the frustum, and for the curved surface area as well, you find the difference of the curved surface areas. Okay, so this is what it looks like. This is the frustum that we have, and it's made out of a cone like this. All right, so sometimes you have to do calculations based on this as well. The idea is the same. You use the same formulas as before, but for finding volume, you subtract the smaller cone's volume from the bigger cone's volume. For the surface area, you subtract the smaller cone's surface area from the bigger cone's surface area. And these cones are also similar. So if you talk about this smaller cone and the bigger cone, these are similar figures. So you can use similarity in some cases as well. If you have the volume of one cone given and the length of radius of both the cones given, let's say, you can use ratios as well to find the volumes of these cones using the similar figures that you have in this case. The ratios of volumes are going to be equal to the cube of the ratio of the sides. That's one kind of frustum that you would see. Another kind of frustum that you would see would be from a pyramid. That's something that can also happen. In this case as well, if you were to extend all of these sides, all of these 4 sides that you have, they will all meet at one point like this. So that this big figure is a pyramid, right? So this whole figure now, this is a pyramid. How is this frustum made? This frustum is made by taking out this smaller pyramid, the one that I've shaded in yellow. This frustum is made by taking out that smaller pyramid from the big pyramid. So if you had to find the volume of this frustum, what you would have to do would be, you would find the volume of the big pyramid and subtract from that volume of the smaller pyramid. Okay, so this is another kind of shape that you will see sometimes. You need to know how to approach this as well. And then one other kind of shape that you would see would be combinations of different shapes. So in a frustum, you basically have one part of a shape, right? So you basically break one shape down into multiple parts. But then you can have combinations of shapes like this. This is a combination. You have a cylinder, right? You've got this cylinder in yellow, and you have a cone attached to the top of this. You have a cone on top like that. If you had to find the volume of this complete figure, you would find the volume of each of these shapes separately. You'll find the volume of cylinder, you'll find the volume of cone, and you would just add them up together to find the total volume. For the surface area, however, you need to remember that the surface area is only for the outer part of a shape. It's only for the external part of a shape. So if you had to find surface area of this shape, for that, you would not be considering this particular circle because this is inside the shape. It's not external to the shape. right? So this particular circle will not be considered in the surface area. So the surface area for this shape would just be the curved surface area of the cone, the curved surface area of the cylinder, and this circle on the bottom. You will find each of these three areas separately. For the curved surface area of cone, you would use pi RL. For this, you would use 2 pi RH. And for the circle, you would use pi r squared, and you would add all of them up together to find the total surface area of this shape. Okay, so these are some shapes that you will see in some questions as well. This can happen. You use the same formulas that you've used for the standard shapes, but sometimes you would have to add one volume to another volume, or sometimes you'd have to subtract one volume from another volume, like in case of a frustum. Okay, just keep that in mind. And one last thing that you'll also see in some questions before we move on to the past paper questions. You sometimes have a sector that is given. You'll see multiple questions like this in past papers. Let's say you have a sector that looks like this. You've got this sector. Now, it does not necessarily have to be a major sector every time. It could be this a minor sector as well. That's also possible. But what happens is they sometimes make a cone. So this is a 2D figure, right? This is a sector. It's a two-dimensional figure. What they can do is they can roll it in such a way that you get a cone out of this. And that's a three-dimensional figure. So they can roll it in such a way that it ends up becoming a cone that looks something like this. Now, how does that happen? Try to visualize that you have a sector like this. Think of a paper in this shape. And then what you do is you basically join these two sides. You join these two sides so that this side, so this radius and this radius, they come on top of each other. Okay, so you kind of combine, join them together. Okay, what happens when you do that is in this cone-like figure, when you join these two radii, you would have one side here on this side, another side here. These two sides are going to be, let me actually make it bigger because the size is not appropriate for that. Or what I'll do is I will just show you an animation for this that might be easier to understand. Let me see if I can find one. I'm just thinking how to show this because I don't have another camera that I can use to show this to you. Let me find an animation to help you understand what it might look like. Okay, maybe I'll share that with you. I'll share that with you in the group, an animation for this that might help you understand. For now, this is, think of it this way, you can remember it this way, that you have one radius here and you have another radius here. What happens is when you convert it to a cone-like figure like that, this radius and this radius, they are going to become the slant height there. So this R is going to go here. You can actually use numbers here. Let's say this value of the radius, let's say this is 10, and this value of the radius is also 10. When it goes and becomes that cone in 3 dimensions, what happens is the slant height of that cone, that becomes 10. Okay, so this radius in that cone becomes slant height. So what you're doing is you're putting these radii on top of each other. And now what happens with this arc length is, in 3 dimensions, this arc length, when you make a cone out of this, by joining these two yellow sides, this arc length goes and becomes this circumference of that sector. So if, for example, this is the arc length, this will go and for the cone, this is going to become the circumference of the cone. So if you have some information given about the sector, for example, you have the angle of the sector, and you can find the arc length of the sector from that, what you can do is you can use that to basically find the circumference of the cone that you would get. Okay. So the arc length of that cone, arc length of that sector, it becomes the circumference of that cone, and the radius becomes the slant height of that cone. Now that's something that you can remember. I'll share an animation with you in the group, which will show you how it's actually done in 3 dimensions. So the radius of the sector, that basically becomes slant height of the cone. And the arc length of the sector, that goes and becomes the circumference of that cone. It becomes the circumference of the circular base of the cone. Okay. Let's take an example of this, and that might help you understand how this is tested. Yeah. So this is from that worksheet that includes cone questions. Let's have a look at this. It says P and Q are points on the circumference of a circle, center O, radius R. The minor arc PQ is 20 centimeters and POQ angle is 48 degrees. Show that R equals 23.9. Okay, now that's the first part. Let's have a look at some questions now. So I'm doing this the first question because it will cover that concept as well, how a sector is converted to a cone like this. Let's think about this. So we have points on the circumference of a circle P and Q like this. We are given the arc length, that's 20, and we're given this angle, this is 48 degrees. We need to find R. What's R? R is the radius of the circle. How can we find that? We have a formula for the arc length. The arc length formula works like this. It's theta over 360 times 2 pi r. Right? The circumference of whole circle is 2 pi r. We're just finding proportion of that. Theta over 360. That's the formula that we've got for that. We know that the arc length is 20. So we can say the arc length PQ is 20. That should equal the angle, which is 48, divided by 360 times 2 pi r. All right. And now you can just evaluate this and see what this turns out to be. 360 goes to the other side, gets multiplied in the numerator. 48 goes to the denominator. And this 2 pi also goes to the denominator there on the other side. R equals this thing. Now you can input this whole thing on a calculator. They want a decimal answer. So you can put this whole thing on a calculator and see what that gives you. 20 times 360 divided by 20 times 360 divided by 48 times 2 pi. And that gives me 23.87 That rounds off to 23.9 to three significant figures. That's the first part, fairly straightforward. We were given the arc length and we had to find the radius. We just input values in the formula for arc length and we got the value of radius from that. Now we need to calculate the area of the minor sector POQ. Area of the minor sector POQ. How can you do that? What's the area formula for a sector? It's theta over 360 into pi r squared. Now, it's not necessary to write the formula. You can just input values in the formula directly and write down the answer after that. But what's this going to be? 48 is the angle divided by 360 times pi r squared. That would be pi into 23.9. That's the radius that you found in the previous part, whole squared. And that should give you the area for this figure. Let's see what that turns out to be. 48 divided by 360 times pi into 23.9 whole squared. And that gives us 239.3 239.27. Now you round it off to three significant figures because this is not an exact answer, right? You round it off to three significant figures and that will give you 239. That's the result that you get from this. Okay, let's move on. Now it says the minor sector POQ is removed from the circle. So you have a circle, you have the circle. This minor sector is now removed from the circle. Now that it's removed, the remaining major sector is shaped to form an open cone of radius r centimeters. We need to find this radius. Now remember what we discussed about this. What happens when this figure goes and becomes this cone? The radii that you have in this cone, this r, this basically becomes the slant height here. In that cone, this becomes the slant height. We have found the value of r before, that's 23.9. So we know that r is equal to 23.9. That means the slant height in this figure is supposed to be 23.9. This is also 23.9. So we know that the slant height of this cone is 23.9. And what about the arc length? What does arc become in that figure? The arc length of the sector, that becomes, this arc length becomes the circumference of the circular base of the cone. It becomes the circumference of that. All right, now do we know what this arc length is? We know the arc length for the arc PQ, the minor arc PQ. We just don't know that part. This part is 20, okay? But we do not know the rest of it. We don't know what this is, okay? But we can find that because we have all the information that we need. This is 48 degrees. One idea could be that you could find the circumference of the whole circle, 2 pi r, subtract from that this part 20, and you would get the remaining part. That will be the major arc. That's one idea. The other idea could be that you could find this angle. If that angle is 48 degrees, what is the remaining angle going to be? This angle would be 312 degrees, 360 minus 48. What does that give you? The major arc PQ, that is equal to 312 divided by 360 into 2 pi r. What do we get from this? 2 pi into 23.9. This turns out to be 312 divided by 360 times 2 pi into 23.9. And that's giving me 130.146. Okay, this is not the final answer yet. That's why I'm using more decimal places here. So we have 130.146. That's this arc length, this major arc. That's 130.146. Now, what happens when this major arc goes and becomes a cone? When the sector goes and becomes a cone like this arc is going to be the circumference of this cone, of the circular part of the cone. Now, using that, what we can do is we can find this radius because now we have a circle on the right side. This circle has a radius of r. If the radius is r, what is the circumference going to be? The circumference is going to be 2 pi r. That 2 pi r should be the same as what we have found here. It should be equal to 130.146. Right? Because that arc length is becoming the circumference. And now we can find the value of r from this and see what that turns out to be. 130.146 divided by 2 times pi, and that gives me 20.7. That's the radius of the cone that we have there. That's 20.7. That's what you can write here. That's the radius of that cone. Does that make sense? Any problems with this? Okay. So that's what happens when you make a cone using a sector like this. Okay. Let's move on to the next one now. It says, calculate the curved surface area of cone A. Cone A has radius 7.5 centimeters and height 4 centimeters. Is it the same cone? No, it's a different cone now. This cone has a radius of 7.5 and the height of the cone, the vertical height, that is 4 units. Calculate the curved surface area of cone A. How can we do that? What's the formula that we've got for that? Pi RL, right? They've given that formula as well. Pi RL. Okay, now what information do we have here? We know the value of the radius. So we can say radius is 7.5, but the problem is we do not have the slant height. Slant height is not given, right? How do you find the slant height now? We know the perpendicular height. This is 4 units. That is something that we know. The radius is 7.5. That means this length or the length on the other side, this is 7.5. Using this, can I find this hypotenuse? It's a right angle triangle, right? I can find the hypotenuse from that. That will be the slant height. So we can say L squared, that's the hypotenuse squared. That should equal 4 squared plus 7.5 squared. Okay, using Pythagoras, we can find the value of L like this. L squared equals 16 plus 7.5 squared. That is 72.25. Take square root of that and see what that turns out to be. That's 8.5. That means the slant height is 8.5. Now we can input that value here. This is 8.5, and that is going to give us the curved surface area of this cone. Let's see what that turns out to be. Pi into 7.5 into 8.5, and that is 200.276 and so on. You can say 200.28. If you round it off to 3 significant figures, that would be 200. That's what you can write here, 200 centimeters squared. That's your final answer. All right, let's move on. Now it says cone B. There's some other cone B that is geometrically similar to cone A. So cone A and cone B, they are similar figures. The ratio of the curved surface area of cone A and curved surface area of cone B is 64 to 25. Find the height of cone B. Now, how do we think about this? They've given something about area. The surface area, its ratio is 64 to 25. Height is a side of the cone, right? That's one length of a cone. What's the ratio between areas and sides in similar figures? We can say A1 over A2, that should equal H1 over H2 whole squared, right? The ratio of areas is equal to square of the ratio of any sides. All right, now let's call cone A. Let's call the area of cone A, A1. And let's call this A2. What's the ratio? 64 to 25. Right? Cone A to cone B, that's 64 to 25. So on the left side, you have 64 over 25. On the right side now, H1 is the height of cone A. Okay, what's the height of cone A? That's 4. Let's use that as the numerator here. Height of cone B is what we're looking for. We can have H2 here in the denominator. We just need to solve this, and that should give us the value of H2. All right. Now, we can take square root on both sides. When we take square root on both sides, we get something like this. Square root of this, square root of this. We just take the positive value in this case because we're talking about lengths, heights. They cannot be negative. So we only consider positive values. What's the square root of 64 over 25? Square root of 64 is 8. Square root of 25 is 5. So on the left side, we get 8 over 5. On the right side, square root gets cancelled with the square, and we're left with 4 over H2. And what's the value of H2 now? Let's take H2 to the other side. 5 goes to through the right side and becomes 4 times 5. 8 comes down here, divided by 8, 20 over 8. That would give us 2.5. You can do this on a calculator if you want. 20 over 8, that is 2.5. That's the height of the other cone that we were looking for, 2.5 centimeters. All right, let's move on. So that was this question. That was 5 and 7, a 12-mark question. Okay. All right, let's move on now. Let's do another question on 2D first, and then we do some questions on cylinder and prisms and spheres. But let's do that question that you asked about earlier. Let's do this one first. Okay, this is from the 2D mensuration worksheet. We have a diagram that looks something like this. It says the entrance to a zoo has this sign above it. Okay, this is the entrance to, so you have some entrance to a zoo and it has this sign on top. The letter Z has a rotational symmetry of order 2. Okay, now I'm assuming you know symmetry, right? Because that's not something that we have discussed before, and you said that you're okay with that. So it says rotational symmetry of the letter Z is of order 2. Okay. Now, what does that mean? Rotational symmetry of order 2. That means if you were to rotate this letter Z, rotate this letter Z. So when you rotate this letter Z, for example, if you rotate it 90 degrees, this part would come here, right? And this part would go here if you rotate 90 degrees. If the rotational symmetry is of order 2, what that means is one full circle is 360 degrees, right? One full circle is 360 degrees. If the order is 2, that means if we divide 360 by 2, we get 180 degrees. If we rotate this figure by 180 degrees, we would get the same figure back from that, right? If the rotational symmetry has an order of 2, that means if we rotate that figure by 180 degrees, we would get that same figure back from that. So if we were to rotate this part 180 degrees, it would go and become this part. And this lower part, that would go and become that upper part. All right. If the rotational symmetry was of order 3, for instance, then that would mean that you would get the same figure again after rotating it by 120 degrees. So think of a fan, for instance, that has 3 wings. A fan, a regular fan, has a rotational symmetry of 3. Why? Because if you rotate it 120 degrees, you get the same figure back from that. In this case, the rotational symmetry has an order 2. That means if you rotate it 180 degrees, you get the same figure back. So that is basically the examiner's way of telling you that this part here of the figure and this part of the figure here, they are identical to each other. They are congruent to each other. Okay. That's why they have given this to you, that this part and this part, they are congruent to each other. Because when you rotate it, this part exactly maps onto this part, right? And the upper part exactly maps onto this part, so they are congruent to each other. What else are we given? DE is perpendicular to FE. DE, where is DE? DE is this. This is perpendicular to FE. Okay, so we have a right angle here. This angle is 90 degrees. CD is 35 centimeters. This is 35. FE is 50. DE is 10. BC is 81. BC, this part is 81. This side is 81. The perpendicular distance between BC and GF is 10 centimeters. You can see that here. The perpendicular distance between this side and this side, that is 10 centimeters. This is all the information that we have given. We have represented that on the diagram. We need to find the area of the letter Z. Okay, how do you find the area of this letter Z? We can break it down into multiple parts, right? How do you break it down into multiple parts? They've already actually done this for you. This is one part that you have. What's this shape? This is a trapezium. Why? Because we know this angle is 90. That means this angle here is also 90, right? These two are exact same shapes. Let's actually focus on the lower one first. This trapezium, one side is 50, the other side is 35, right? So two parallel sides, they have lengths 50 and 35 respectively. The distance between them is 10. So we have the height of this trapezium as well. We can find the area of this trapezium, right? Let's find that first. Area of trapezium DCFE. What would that be? Half into sum of parallel sides, which is 50 plus 35 times the height. Height is 10. And that should give you some value. Let's see what that is. 85 times 10 divided by 2. This is 425. Now, if this area is 425, it's also the same as the area on top there, right? Because these two are congruent figures. So we have these two trapeziums areas. What we're left with is the area of this figure. Now, what exactly is this figure? What exactly is this figure? This is actually a parallelogram. How do we know that? Because of the rotational symmetry again. When you rotate this figure, what happens is this line is going to map exactly onto this line. And this side of this figure, BC, when you rotate it 180 degrees, on the other side, it's going to map exactly onto this side, where is GF. Which means these opposite sides, they are equal and parallel. This is a parallelogram, okay? This part is a parallelogram. What's the area of a parallelogram? Area of a parallelogram, that's just base times height, right? Now, do we have the base? So if we consider this side as the base, it has length 81. Height is going to be perpendicular to that. That's 10. So we can just find the area of this parallelogram and see what that turns out to be. Area of the parallelogram BCFG, right? That's the parallelogram that we're talking about, BCFG. That's base into height. Base is 81, height is 10, and that gives you 810. That's the area of this parallelogram. What's the total area then? The total area of this figure? There are two trapeziums, the green ones. One has area 425. You multiply that with 2. So that's the area of this trapezium at the bottom and the area of the trapezium on top, right? One has 425 area, so we multiply that by 2. Add to that area of that parallelogram, that's 810. And that should give you the result. That's 850 plus 810, and that will be 1660. That's the area that we were looking for. Okay, that's the first part. Now it says the shaded area of one letter O is 1206 centimeters square. Okay, so this is the shaded area of the letter O. We can see that. The radius of the unshaded inner circle is 15. Calculate the radius of the outer circle. Okay, now let's think about this. Shaded area is 1206. Have they given us any information about O? Do they tell us anywhere it's a circle? Okay, yeah, so they're telling us here that's a circle. These are both circles. So this figure O, this is a circle. It's made up of two circles like this, right? We are given that the shaded area is 1200 and something. It's 1206. That's the area of this part. Okay, and we're given the radius of the smaller circle. That's 15 centimeters. So this length is 15 centimeters. We want to find the radius of the bigger circle. How can we do that? How can we find the area, the radius of the bigger circle now? That's the question. Now let's think about it. Area of the shaded part, it's going to be area of the bigger circle minus the area of the smaller circle. Can we find that area somehow? Pi r square is the formula that we've got for that, right? Let's call the radius of the bigger circle r. Then the shaded area in this case would be, shaded area would equal pi r squared for the bigger circle. You can say pi into r squared minus the area of the smaller circle. That would be pi into 15 square. That's the radius of the smaller circle. That's the shaded area. They're telling us that the shaded area is 1206. So we equate this to 1206, and that gives us pi r squared minus 225 times pi. That equals 1206. Now we want to find the value of r from this. How can we do that? We can take this to the other side. That gives us 1206 plus 225 pi equals pi r squared. Divide pi on the other side. That would give you 1206 plus 225 pi divided by pi. That equals r squared. And then just put square root in that whole thing. And that will give you the value of r. Let's see what that turns out to be. Square root of 1206 plus 225 pi divided by pi. Okay, you can input this whole thing in your calculator like this, making sure the square root is on that whole thing. And inside that whole thing, you've got a fraction like this. The radius turns out to be 24.675. You can say that that rounds off to 24.7. That's the radius of the outer circle, 24.7. And that's what we were looking for. Okay, let's look at part C now. The sign above the exit of the zoo is geometrically similar to the one above the entrance. Okay, so this was the sign at the entrance. There's another sign at the exit as well, and that's geometrically similar to this. The radius of the inner circle of the letter O on the sign above the exit is 10 centimeters. Okay. Radius of the inner circle of that similar figure, that is 10 centimeters. The length of the base of the letter Z on the sign above the entrance is 50 centimeters. Okay, length of the base of the letter Z on the sign above the entrance. Okay, we already know this is 50 centimeters. Okay. Calculate the length of the base of the letter Z on the sign above the exit. Okay, now how do we think about this? Radius is a length, right? Radius is a side, and length of the base, that's also a side. In similar figures, the ratios of sides are equal. So we can say radius of the inner circle, let's call that. So we're talking about entrance and exit, right? Let's call number 1 entrance and number 2 exit. Okay, so what we're talking about is ratio of the radii that should equal ratios of the lengths of the bases. Now, what are we looking for? R1 is the radius of the inner circle on the entrance. Do we have that? Radius of the inner circle, that's 15 for the entrance. Let's input that value here. Radius of the inner circle on the outer, on the exit, that's 10. So 15 over 10, that's the ratio. That equals length of the base of the letter Z on the sign above the entrance, that's 50. L1 is 50 in this case. Divided by L2, that is what we are looking for. That would give you L2 equal to 50 times 10 divided by 15. You can see what that turns out to be. 500 divided by 15, that is 33.3 centimeters to three significant figures. You can you can write it as 100 over 3 as well. That's also acceptable. Or you write that as 33.3 to three significant figures. Okay, let's move on now. It says the area of the sign above the entrance is A centimeters squared. The area of the sign above the exit is Ka centimeters squared. Write down the value of K as a fraction in its simplest form. Okay, now we're talking about areas. For similar figures, areas are supposed to be, the ratios of the areas is supposed to be equal to the square of the ratios of sides. So we can say A1 over A2 is equal to L1 over L2 whole squared. Now, entrance we're representing with letter 1, with number 1. So we can say this is A1. A1 is equal to A. This is A2. A2 is equal to K times A. That's what they're saying. L1 is one side of the entrance. So we have this ratio already, right? 15 over 10, we can use that. This is the ratio of the radii. We can use that because the ratios of all sides are going to be the same. 15 over 10, let me use that here. 15 over 10 whole squared. Now, A1 is supposed to be A. A2 is supposed to be K times A. And from this, we can find the value of K. Let's see what that turns out to be. A and A get cancelled, and we are left with 1 over K equal to 15 over 10. We can cancel it out. This becomes 3 over 2, which is 9 over 4, right? 3 squared is 9, 2 squared is 4. So that's 1 over K equal to 9 over 4. What's the value of K going to be? This is 1 over K, right? We can take reciprocal on both sides. That will give us K equal to 4 over 9. That's what we write here. The value of K is 4 over 9. Does that make sense? All right. Okay, so that was this question from this worksheet. Let's move on to a few other questions now. Let's do some 3D mensuration questions. Okay, this looks like a good one. Let's start with this. A birthday cake is in the shape of a cylinder. There are 2 layers of cake and 1 layer of icing. Each layer of cake has radius 10 centimeters and height 3 centimeters. Okay, so you have icing and then 2 layers of cake. This is the layer of cake. This is another layer of cake. And in the middle, you've got some icing. Icing has radius 10 and height 12 millimeters. Now notice the difference between the units. You have to be careful about that. Calculate the volume of icing in the birthday cake. Give your answer in centimeter cube. Now, for the icing, you are given this number in millimeters. How do we convert it to centimeters? Millimeter to centimeter, what's the ratio? 1 millimeter is 0.1 centimeters. Or you can say 10 millimeters are 1 centimeters. So if you have to go from 12 millimeters to centimeters, you can say that's 12 over 10 or 1.2 centimeters. Okay, that's the height. What's the volume of icing? It's a cylindrical shape, right? What's the volume of cylinder given by? It's pi r square h. Just input values in that. Pi into r, radius is 10, into pi r squared into h is 1.2. And that's it. That should give us the result. 100 times 1.2 times pi, and that gives us 120 pi. In decimals, that would be 376.99. We rounded off to three significant figures because this is not an exact answer. And that gives us 377. That's what we write here, 377. That's the final answer that we get. Okay, let's move on. It says the top and curved surface of the birthday cake are now covered with chocolate. Okay, the top surface and the curved surface. They're now covered with chocolate. So it's the top surface, it's a circle, and the whole of the curved surface on the side. Calculate the area of the birthday cake that is covered with chocolate. Now we have a circular top. What's the area of that circular top going to be? Pi r squared. That's the area of this yellow part. Plus this curved surface area. What's the formula for curved surface area? It's 2 pi r h for a cylinder, right? That's the area of the curved surface on the side. Now the curved surface is going to be all of these three parts, right? You will include icing in that because they're talking about birthday cake. The whole of the cake is covered, right? The sides and the top. That includes the icing. All right. What is this going to be? For the circular top, pi r squared, we say it's pi into 10 squared, plus for the curved surface part, that's 2 pi into radius, that is still 10, times the height. What's the total height? We have 3 centimeters, and then 1.2 more. That becomes 7.2. So we multiply this with 7.2, and that should give us the total area that's covered by chocolate. You can see what that is. 100 times pi plus 2 into pi into 10 into 7.2. Okay, and that gives us 244 pi. They don't want an exact answer. We can write this in decimals. That's 766.55. Round it off to three significant figures, and that would be 767 as your final result. Okay, and that's what we were looking for. That's part B. Let's move on. Anil has a slice of this chocolate-covered birthday cake. His slice is a prism of height 7.5 centimeters. Now, they have clearly told us that it's a prism. Even if they had not told us that it's a prism, we should have been able to figure that out because it is the shape of a prism. We have two opposite faces that are identical and parallel. One is this face on top, and the other is this face on bottom. These two opposite faces are equal and parallel, and they're joined by straight lines. Right? That's what a prism typically looks like. Two opposite faces that are identical and parallel to each other, and those two faces are joined by straight lines. Okay? That's what's happening here. What's area of prism given by? Area of prism is base area into height. Base area, or you can say area of cross section times the height. Okay, base or cross section, this identical face that you have on both sides, this is called the base or the cross section. And the height is the distance between those two faces, that is 7.5. All right, now they've explained that the top of the cake is a sector, radius 10.3 centimeters, and angle x calculate the value of x, given that the volume of the slice is 200 centimeter cube. Now, what's the volume of a prism given by? We wrote that above. It's the base area into height. What's the base area? Base is the sector, right? What's the area of a sector given by? Area of a sector is theta over 360. Theta is x over 360 times pi r squared. That's pi into 10.3 squared. That's the base area. Times the height. What's the height in this case? Height is 7.5. This is going to give us the volume of this piece of cake. They've given us that this volume is 200, so you equate this with 200. And now you can use this equation to find the value of x. Let's see what we get from this. We can simplify this a bit if we want. On the right side, if I simplify this, it becomes x times pi into 10.3 squared times 7.5 whole divided by, or I can just do this, the whole divided by 360, right? The right side is 6.94357. Okay, I'm writing more decimals because this is not the final answer, so we should use more accuracy there. This is what we get on the right side. Now divide this number on the other side. I can say 200 divided by that answer, and that's going to give me 28.8. That's the value of x that we were looking for. The three significant figures, this is 28.8. That's the angle 28.8. All right. That was part C of this. Let's move on. Okay, now let's have a look at another one. This looks straightforward. Should we do this? Volume of the empty space, that will just be cuboid minus the cylinders. Okay, this looks like a good one. Let's do one on sphere, and then we come back to that. We've not done a pyramid one. Let's see if I can find a pyramid question here quickly. Okay, let's do one on spheres, and then we go back and do maybe one more question from there. Okay, let's try this one. This looks kind of weird. Yeah, let's try this. A spoon used for measuring in cookery consists of a hemispherical ball and a handle. You can see that here. The internal volume of the hemispherical ball is 20 centimeter cube. Internal volume, you can see internal volume is going to be for this hemisphere that has this inner circle as one face. Okay, you don't consider the radius as this whole thing. The radius of that inner hemisphere is just this part. The internal volume again is 20 centimeter cube. Okay, the internal volume is given to be 20. The handle is of length 5 centimeters. So this length is 5 centimeters. Find the internal radius of the hemispherical ball. We need to find this internal radius. Okay, so we are given the volume. What's the volume of a hemisphere? Volume of a sphere is 4 over 3 pi r cube. For a hemisphere, it's half of that. That's 2 over 3 pi r cube. Okay, they have given that the volume is 20. So equate this to 20. We get 20 equals 2 over 3 into pi r cube. And we can find the value of r from this. 20 times 3 is 60. 60 over 2 is 30. 30 equals pi r cube, or let's do it directly. 20 times 3 divided by 2 pi, that equals r cube. And then you can find the value of r by taking cube root on both sides. R equals 20 times 3 divided by 2 times pi. And then it is take cube root of that. Cube root of this number. Radius is 2.1216. To three significant figures, that would be 2.12. That's what you write here. 2.12. That's the radius of that hemispherical part inside. Now, the hemispherical ball of a geometrically similar spoon has an internal volume of 50 centimeter cube. Find the length of its handle. Okay, now how do we think about this? We have two similar figures. We're talking about their volumes. What's the ratio of volumes and sides? V1 over V2. That is equal to L1 over L2 whole cube. Ratio of volumes is equal to cube of the ratio of sides. Let's call the original one figure 1. For this, we know that the internal volume is 20 and the length is 5. So 20 over something, that equals 5 over something whole cube. For the other figure now, what's the volume? Internal volume of this spoon is 50. So we write 50 here. This length of the handle is what we're looking for, L2. That's what we have to figure out. Okay, now how do we do this? Let's simplify this. On the left side, 2 and 5, they get cancelled. On the right side, we can do it like this. 5 cube is 125. That divided by L2 cube. Okay, let's cross multiply. L cube equals 125 times 5 divided by 2. And then it just take cube root of that on both sides. That will give you that length that we are looking for. 125 times 5 divided by 2. That's this number. Now, take cube root of this. And this turns out to be 6.786. If you round that off to three significant figures, that would be 6.79. And that is your final answer, 6.79. Okay. That was the second part of this. Let's move on. Now it says the surface area of a sphere is 4 pi r squared. An open hemisphere of radius 5.5 centimeter is used to make a metal kitchen strainer. All right. Open hemisphere of radius 5.5. So we know the radius of this hemisphere. 50 holes are cut out of the curved surface. You can see that you have these holes cut out of this curved surface. Assume that the piece of metal removed to make each hole is a circle of radius 1.5 millimeter. Calculate the external surface area that remains. Okay, now how do we think about this? The top is open, so we don't have to consider the circular top. Okay, the surface area is just given by this curved part. Okay, now the curved surface area of a sphere is 4 pi r squared. What about a hemisphere? Curved surface area of a hemisphere is given by 2 pi r squared. Okay, we just halve that. 4 pi r squared divided by 2, that's 2 pi r squared. Can we find this? Radius is 5.5. That would be 2 pi into 5.5 whole squared. Let's see what this turns out to be. 2 into pi times 5.5 squared. And that is 190.066. Okay. If there were no holes there, this would be the surface area that we were looking for, right? This is the curved surface area without the holes. But now we know that there are 50 holes like this, and each hole is a circle of radius 1.5 millimeters. Okay. Let's first convert it to the same unit. We're talking about centimeters here. 1.5 millimeters, 1.5 divided by 10, it would become 0.15 centimeters, right? That's the radius of each of these small circles. It'll be 0.15 centimeters. Let's find the area of these 50 circles. Area of those 50 small circles. Let's see what this turns out to be. Pi r squared, right? So pi into 0.15 whole squared. Let's see what this is. 0.15 squared times pi, that is 0.070686. But we're talking about 50 small circles. What we can do is we can just multiply this whole thing with 50. Let me just do it in the same line here. 50 into this whole thing. Let's multiply this with 50 as well. That gives us 9 over 8 pi, or in decimals, that's 3.534229. Those small holes, they have this area, 3.53429. What we can do now is we can subtract from that total area. We can subtract from that the areas of these holes and the external surface area that we are left with now. The final external surface area, that would be the difference of these two numbers, 190.066 minus 3.53429. Let's see what this turns out to be. 190.066 minus the answer, that gives me 186.53. If you round it off to three significant figures, that gives you 187. That is the final result that you've got here. The area, the external surface area of this figure is 187. And that's what we were looking for. Make sense? Any problems with this? All right. Let me see if I can find us one more small question, and then we end for today. Yeah, so let's do one where we don't use a calculator. So from the non-calculator paper, let's do one or two from here quickly. Let's find one on pyramid first. Okay, this looks like a good one. Let's try this. This is question number 40 from this non-calculator worksheet. It's that frustum that we talked about, right? It says the diagram shows a solid pyramid L cut into two parts. The base of pyramid L, the first one, is a rectangle 9 centimeters by 12 centimeters. This base, it's a rectangle. The perpendicular height of pyramid L, the first one, that is 30 centimeters. Height is 30 centimeters. Work out the volume of pyramid L. Okay, this whole pyramid, work out the volume of this. What's the volume of a pyramid given by? It's given in the formula sheet that you get in the exam as well. 1 over 3 into base area into height. So 1 over 3 into area of base. What's the base area in this case? It's a rectangle. That will just be 12 into 9. That's the base area. Times the height. What's the height? Height is 30. that gives you the volume. Now, this is from a non-calculator paper, so you're not allowed to use a calculator for this calculation. Let's do this manually. We can do some cancellation, right? 3, we can cancel this out with 30 to get 10 from this. And then 12 times 9, what's that? 12 times 10 is 120. 120, you can subtract what 12 from that, that's 108. Or you should just remember your tables well. 12 times 9 is 108, okay? So you have 108 from here times 10, that's 1080. That's the volume of this pyramid, 1080. Now it says the perpendicular height of pyramid M is 1/3 of the perpendicular height of pyramid L. This is pyramid M, that's a smaller pyramid, so they've taken out of that pyramid. And that has a height that is 1/3 of the first one. What does that mean? This was 30. 1/3 of that, 30/3, what does that become? That becomes 10. This smaller pyramid has a height of 10, sorry. 30/3, that's 10. Express the volume of M as a fraction of the volume of L. Volume of M as a fraction of the volume of L. Okay, how can we do that? These are similar figures, right? We can just use the ratio. We don't have to use this, do the whole calculation. It's just a 1-mark question. Yes, one idea could be to try and find the volume of this smaller pyramid, but that will be quite long. You'll have to find the area of the base, first of all, for which you need these lengths, and that will take quite long. You can use similarity of these figures. Let's call, okay, in fact, we already have their names there, so we can say volume of pyramid L over volume of pyramid M, that should equal height of pyramid L divided by height of pyramid M whole cube, right? That's the ratio in case of similar figures. We want to express the volume of M as a fraction of volume of L. Okay, we'll do that. Height of pyramid L, what was that? That was 30. So it becomes VL over VM. That equals 30 over height of pyramid M, that's just 10, whole cube. This gets cancelled, and we're left with 3 cube, which is 27. VL over VM, that is equal to 27. Okay, now what are they asking for? They want us to express the volume of M as a fraction of volume of L. I should have read this earlier to basically switch these. That would have made this quicker. But if you've done it this way, with volume of M in the denominator, now what I can do is I can take this to the other side, bring 27 here, and that basically gives me, okay, I'm sorry about that. That's question 40, right? Okay, I can take VM to the other side and bring 27 here, and that gives me 1/27 times VL. So volume of pyramid M is 1/27 of VL. And you can write that here, that's 1/27. A quicker way of doing this would actually have been, since we know that the perpendicular height is 1/3 of the perpendicular height of pyramid L, the ratio of volume would have just been 1/3 whole cube, right? That's actually much quicker. And you did not really have to do all of this. You could do it directly. Just thought of that. This is 1/3, right? The ratio of their sides. What about the ratios of their volumes? It would just be 1/3 whole cube. So you could do it directly like this as well. That's 1/27. And that's the result that we've got. Okay. Calculate the volume of the solid N. What's the solid N? This solid. How do you calculate the volume for this? The volume of this solid, it's a frustum, right? Sometimes they use that terminology as well. This is just volume of the bigger pyramid minus the volume of the smaller pyramid. What's the volume of the bigger pyramid? We found that earlier, that's 1080. That's the volume of the bigger pyramid. Subtract from that the volume of the smaller pyramid. That's this pyramid. Now we have already shown in the previous part that the ratio or the volume of the smaller pyramid is 1/27 of the volume of the bigger pyramid. So what would be the volume of the smaller pyramid? That will be 1/27 of 1080. So you can subtract that number from this, and that will give you the volume of this shape here. You can see what this turns out to be. 1080 minus 1080 divided by 27, and that gives us 1040. That's one way of looking at this. Another idea could be the smaller pyramid is 1/27 of the bigger pyramid. So if we consider, for instance, that the bigger pyramid is 1, then this is 1/27. What about this remaining part? This would be 26/27. So you could directly do it like this as well. You could say 26/27 times 1080. That would also give you the same result. So basically that would be 26/27 times 1080. That's also 1040. That could be another way of thinking about the same thing as well. Okay, that gives it the same result. You could also do it this way. All right, I hope that makes sense. Let's do one last question. I want to do one in which they want the answer to be in terms of pi. Okay, in this case, r is also unknown. Also r and pi. Okay, let's do one of these. The one that I saw in the beginning. Okay, let's try this. This one last question, then we end. The diagram shows a sector of a circle with radius 3r centimeters. So sometimes they would want you to give your answer in terms of pi. In that case, just make sure that you don't put pi on your calculator to convert it to a decimal. Just do your working in terms of pi. Okay, now let's see how that would be done in this using this example. The diagram shows a sector of a circle with radius 3r centimeters and angle A, and a circle with radius r centimeters. The ratio of the area of the sector to the area of the circle with radius r is 8:1. Find the value of A. Okay. We have the ratios of the areas. Remember, these are not similar figures, so we can't use those similar figures ratios. Let's find the area of the sector first. What would that be? Area of the sector. Area of sector is theta over 360. That's A over 360 times pi r squared. Pi into 3r whole squared. Okay. Let's simplify this. Remember, it's the non-calculator paper. You cannot use your calculator. This gives you A over 360 times 3 squared is 9. So pi into 9r squared. Let's do some cancellation. 36 and 9, you're left with 4 here. So 40, that's 40 basically. This turns out to be A pi r squared divided by 40. All right, that's the area of the sector. What's the area of the circle? area of the circle is just pi r squared. They have given us that the ratio of these areas is 8:1. That means a pi r squared over 40, whole thing divided by area of the other figure, which is pi r squared. This should equal 8/1, right? This ratio is 8:1. Now, what happens when you do this? This 40 will go to the denominator, right? So that this fraction becomes a pi r squared divided by 40 pi r squared. This 40 goes to the denominator. Pi r squared and pi r squared, they get cancelled. A over 40 equals 8. 40 times 8, 4 times 8 is 32 and 0. That's 320. The value of A turns out to be 320 degrees. That's what we were looking for. Okay. Now it says find an expression in terms of pi and r for the perimeter of the sector. Perimeter of the sector. What's the perimeter of the sector? There are three sides to this. One this, another this, and then this. Right? 2 radii and 1 arc length. What's the arc length formula? Theta over 360. A is 320 now, we know that. Over 360 into 2 pi r. That means 2 pi into the radius. What's the radius of the sector? It's 3r. Don't forget, it's not r, it's 3r. 2 pi into 3r. Okay, now let's simplify this and see what that gives us. 0 and 0, they get cancelled. And then 36 and 3, that leaves me with 12. 12 and 2, that leaves me with 6 here. And then 6 and 32, that leaves me with 3 and 16. So I have 16 in the numerator and 3 in the denominator. So this simplifies to 16 pi r divided by 3. That's the arc length. That's the arc length. Okay. What's the perimeter going to be? Perimeter is this arc length. Perimeter is the arc length, which is 16 pi r over 3 plus the radii, which are 3r plus 3r. What do we get from this? 6r. So this is our final result. 16 pi r divided by 3 plus 6r. And that's what we write here. The perimeter is given by 16 pi r over 3 plus 6r. And that's our final result. That's the perimeter of that sector in terms of pi and r. All right. Any problems with this? Any questions, anyone? No problems? All right, so that's it on mensuration then. In the next class, now we'll start another major topic, one of those transformations, vectors, graphs of functions, or differentiation. That's what we will be doing next, one of those topics. But that's it for today. I'll see you again in the next class. Allah Hafiz.